So oxidation number we have been discussing, and there is another term called valency which was initially used. So valency basically is a complete whole number, whereas oxidation number may be a fractional value. Valency is a number, it can never be zero, it is just a number without any charge, whereas your oxidation number could be negative, positive, zero, fraction. Alright. So of late we have been using oxidation number, but initially we were using valency. So valency tells us about the combining capacity, whereas oxidation number is the number you get when you break all the bonds attached to a particular atom. For example, if I want to check oxidation number of oxygen in water, so what I will do is I will break all bonds attached to oxygen. For example, we have water like this. I want to check oxidation number of oxygen in this molecule. What I'll do is I'll break all bonds attached to oxygen. I'll break this bond. Oxygen is more electronegative, so it will get -1, and this is less electronegative, so it will get +1. Similarly, I'll break this bond as well, so this will get +1 and this oxygen will get -1. In total, oxygen has charge of -2. So oxidation number of oxygen out here in water, if anybody asks me oxidation number of oxygen in water, so I'll tell them the oxidation number of oxygen in water is -2. Alright, and same oxygen if it is combined with fluorine OF2. So what happens if I break bonds out here? What will happen? If I am breaking this bond, fluorine is more electronegative than oxygen. What will happen? This will get -1 and it will get +1. Similarly, if I break this bond, fluorine will get -1 and oxygen will get +1. So what is the total charge on oxygen out here? Total charge oxygen has +2 over here. So oxygen is same atom, but it has variable oxidation state depending on the molecule, whereas valency for any particular atom remains same. Alright. So oxidation number varies from molecule to molecule. Oxidation number depends on which atom is combined to a given atom, whereas valency is a constant value. Alright. So how oxidation number is obtained and how valency is obtained, I explained to you just now. And there is another term called stock notation. What is stock notation? Stock notation is nothing but mention of oxidation number in Roman numerals just followed by the name of the metal. For example, if I have to write Cu₂O, so oxidation state of copper out here is +2. So how I will write that is, this is basically called as cupric, right? But where in the stock notation we will write Cu₂O as copper. What is the oxidation state? This is -2, this is +2. So oxidation state of copper out here is 2. So I will write 2 in Roman numerals. I have followed wherever we'll write copper, then its oxidation state in the compound, then I will write oxide. And if I have Cu₂O, oxidation state of copper out here is +1. So I will write the name as copper and in brackets 1 oxide. So this representation where you write oxidation number just after the metal name is known as stock notation. Alright, so this is a very simple approach. There is nothing much to be explained. If I have to write Fe₄O, what I should write? I think you will agree with me. The oxidation state of iron, oxygen is -2, so this has to be +2. Total charge in a neutral molecule is always 0. So total negative has to be equal to total positive. So I will write the name for this as iron in the brackets in Roman numerals, of course, 2 and then oxide. Right. Similarly, we have taken a few examples out here. And just remember, if you have copper +1 and copper +2, similarly Fe +1 or +2, Fe +3. So these are common oxidation states of metals which have been observed in compounds. So when copper is in +1, called it call it as cuprous. There is a common name. And when copper is in +2, we call this as cupric. There is a common name I am talking about. As stock notation, we just mention the name of the element like copper. We don't say cuprous or cupric. We say copper, right? When Fe+2 is present, we say ferrous. And when Fe+3 is present, we say ferric. So the higher oxidation state is ic. See, +2 is the highest oxidation state of copper. So we have mentioned it as ic. And his in iron, we have +3 highest oxidation state, we have mentioned as ic. So higher oxidation state is mentioned as ic and lower oxidation state as us. So +1 of copper is cuprous and +2 is cupric. Similarly for iron, +2 is ferrous and +3 is ferric, right? For tin, similarly Sn+2 is called stannous and Sn+4 is called stannic. Alright, so it comes for the higher oxidation state. We have couple of more examples out here. MnO is called manganese oxide, MnO₂ is called manganese dioxide, Mn₂O₃ is called manganese sesqu oxide. The representation is same, metal followed by oxidation number in Roman numerals, and then you have oxide, fluoride, whatever the category of compound is. Alright, and we have couple of examples where fractional oxidation state comes, and here in a sodium tetrathionate Na2S4O6 minus 2, Na2S4O6. So here fractional oxidation state comes, and that is, it is the average oxidation state. As you already know that average oxidation state could be fractional. So we have a average oxidation state out here which comes out to be 2.5. And in the individual oxidation state, if I tell you, then this sulphur has +5 and these two sulphur have 0. So variety of oxidation states are 2, 0 and +5. But average is +5, +0, +0, +5 by 4 sulphurs are there. So +5, +0, +0, +5 by 4. So you get 2.5 average oxidation state. Whereas this is called Marshall state, H2SO8. And the average oxidation state for this comes out to be 5 + 0 + 0 + 5 by 4. Again it will come out to be 2.5. And individual oxidation states, if somebody is asking, you can tell them 5, 0, 0, 0, 5, 0, 0, 5. Or variety or variation in oxidation state is 0 and 5. That is what we have mentioned out here. So this is it for now. Thank you.